area is very green.
So they got one.
Everything
But I
I see is
evolved
like
it. I'm like, I can do all of it.
just really cool. So it's like it's an easy place to explore because everything.
So what do you guys like? What are you mentioning? Levels? Kind of like
I grew up like in a
paragraph. And then, like, you can do like the keywords and then going down to here and then explanations. And it's
All right, 7 o'clock. Time to go.
I don't know what. Yeah. I just.
Okay, so this class is going to be sort of unique in the semester so far, in that we're not going to talk about actual code very much. On Monday, we spent a long time talking about Java and how you do loops. This class is going to be a lot more on, I don't want to say theory, but how you think about problems, how you approach problems, how you solve problems, how you figure out what you're going to do and where to start and what to do next. These are like the central concepts to computer science. When Julie and I were in college, they did a whole course on algorithms in the second half of our freshman year. And essentially before that class, you know, you can do a little bit, you can't do a lot. And after we went through that semester, there were kids from our year, including us, applying for internships, going and getting them, because at that point, you've got the core skills, right? These are the core skills of computer science. Learning how to program in Java, that's extra. Knowing how to reason about problems, figure out what you're doing, like this is the important part. As Julie can attest, who actually took the AP Computer Science exam, you can barely know Java syntax at all, be able to express yourself in terms of algorithms and pseudocode or fake code, and get through the exam by like expressing your ideas and what you mean without actually needing to write specific code, right? This is the important part.
I basically wrote my whole test in English words because I didn't really know how to write Java and I couldn't remember like the right words for it. So I just wrote like, do this thing next, and I got a 5.
This is the important stuff. I'll probably say that again throughout the slides, but this is the critical thing that you want to have when you come out of this class. These are like the thinking skills, the critical thinking skills, the problem solving skills. They're the important bits. So I'm calling them algorithms. What are algorithms? Algorithms are a way to solve problems. You've seen algorithms before in your life. This isn't the first time you're going to see them. It's just the first time, probably, that you're going to call them by this name. It's basically any plan or design for how to solve a problem, fix a problem, accomplish something. Most common ones are recipes. Actually, when we were in school, one of our teachers would frequently use the word recipe as a synonym for algorithm. When you're cooking, you go through this recipe step by step. It gives you instructions. You don't really need to know how to cook that well. You just need to be able to follow directions, which some of the recipes out there, it's kind of dicey, but yeah, that's the idea. Long division, right? How do you divide two numbers where it's not particularly obvious? They give you this step-by-step description for how to do it. You can just go through this procedure. If you do exactly what they tell you, you're going to end up with the result of dividing these two numbers. You don't really have to understand how it works. It sure helps you to remember how to do it if you understand how it works. But it's this procedure that you can go through and it'll work every time. Blueprints for building houses. You know, some architect can come in and build a blueprint, and then a bunch of construction workers can come in, start building the house. Other people can come in and pick up where they left off, right? The blueprint's already there. They know how to build the house. You just have to go and do it at that point. This is the stuff that requires all the critical thinking and problem solving. So, example with cooking. This is the algorithm for pasta. If you don't know how to cook, if you're, I don't know, 6, 7, 8 years old, your mom tells you to cook pasta. You have no idea what you're doing. Step-by-step instructions. First, get some water, bring it to a boil. Second, take the noodles you've got, you stick them into the pot. You stir the noodles. You keep stirring the noodles for the next 10 minutes. You drain out all the water so that all you've got left are noodles. You add some sauce. You're ready to go, right? This is pretty basic so far. I hope everyone's still with me. Right, this is an algorithm. All it is just step-by-step instructions for what do I do. It's concise. I'm not being over wordy. I'm not saying, reach in with your right hand into the box of pasta, close your hand so that you are grabbing the pasta, lift it out of the box, put it over the pot, put your other hand on it, move your hands like this to, no. I'm telling you what you need to know to get this done, right? If you don't know how to bring water to a boil, maybe you have to look up how to bring water to a boil. But these are the basic steps. You don't really need to know why you're doing them. This is enough to get you done. I'm still leaving details to the chef here, right? You probably already know how to boil water. You probably already know how to add sauce to the noodles. I don't need to describe all these things. You can figure out how to do it. If you have a different type of noodle, that's fine. You can adapt this. It just says put the noodles into the pot. I'm not telling you which noodles to use. You can figure that out for yourself. How do you boil water? Maybe you have one of those little handy water boiler machines where you just hit a button and it boils water for you. Maybe you've got to, light a fire and, set up something to suspend your pot over the fire until the water boils. Whatever. I'm not judging. You can figure it out, right? I'm leaving all the details up to you. Works in any kitchen because I'm leaving the details up to you, right? I haven't made it so specific that it doesn't work for someone else. This is pretty much going to work wherever you're cooking pasta. And it's simple enough that you don't actually have to be a chef to know what's going on, right? I could give this to a 10-year-old and they could probably get through all the words. They might have some questions about how to bring water to a boil, but they can get through the words, they can figure it out, they can move through this. I'm not using super technical words or say a different language. So let's do a different example. Let's do something more like something you guys have already seen and done in class. How do we print out the squares from 0 to 10, right? You've already seen the code version of this. I think this was one of the loop examples we did on Monday. It's also one of the array examples we did, I think, getting a bunch of squares from 0 to 10. So we can initialize some integer to 0. We can square it and print out the value, increment it by 1, and then just repeat those steps 10 times so that we print out all 10 squares, right? This isn't Java. It's not really anything computer science-y at this point, except that we're using some variable I. But you use variables like I in math class. I mean, this could easily be mistaken for how to do something on your math test too, or like how to label axes of like a log scale graph or something. This isn't specifically about computer science. It's not specifically about Java. It's just in general telling you how to print out a bunch of squares. So, same things hold for this slide. It's concise. I'm not giving you unnecessary detail. I'm not telling you how to square the number. You can probably figure that out for yourself. I'm not telling you how to print it out. That can be different in different places. Works in any language. And this is pretty simple. Like I said, you could see this in a math class. Someone who's not necessarily a computer scientist can figure out what's going on, figure out the details. But I've still got enough steps on here that you can walk through it. It's going to be the same for everybody. No. Okay, everybody with me so far? Kind of basic. We haven't done any real examples, but I want to make sure that you're following along. So, as a demonstration of the fact that this really works in any programming language, I'm going to do the exact same thing in a bunch of different programming languages. Some of them you've seen, like Java, right? This is essentially what we wrote the other class. I can initialize I to 0. I can repeat 10 times I can print out I squared and then increment I, right? This is essentially what we did last class. Or I could do this differently. I could do it with an array in a loop. I could get all my numbers up front, and then I could just do a for each loop over this array and print out each of the squares, right? This does the same thing. But in that algorithm above that I showed you, it doesn't really specify which one you have to do, right? It leaves it up to the programmer. Which one do you want to do? Which one do you think looks nicer? Which one is going to work better for the style of your code? It kind of leaves this choice up to you. I can do this in something that's not Java. I can do it in JavaScript. I think those of you who took the, what was it, Empoder summer program, I'm not sure what it was called, probably recognize something like this, because I think Julie walked through stuff like this. So maybe, I don't know. You guys might recognize this example. The rest of you, you might be able to figure out what it's doing. I don't know. If you stared at it and squinted for a while, you could probably figure out that this is starting with I at 0, it's going until I is 10, and it's incrementing I each time in between. And then it's just printing out I squared. The statement for printing is a little different, whatever, but it's a different language. The programmer who knows that language will figure it out and learn how to print. I could do this in an even different language. This is BASIC. BASIC is a language that is kind of basic. It was invented a long time ago, and I think it's most famous for, let's see, your calculators. If any of you have like a TI-84 or a TI-89 or something, you can program your calculators with a variant of BASIC if you know how to make like user functions or something. Sometimes your teacher will have you make like a quadratic formula function or something in class. I vaguely remember doing that, but it's a variant of BASIC. So I can do this in BASIC too. Write the same thing, go from 0 to 10, step up by 1 each time and print out I squared. I can do the same thing in Bash, which is another programming language. This time I did something sort of similar to the array thing. I say for each I between 0 and 9, print out I squared. This time print is echo, right? Same thing in Python. This time, I'm actually squaring the number. I'm doing I squared, not I times I, right? Just slight variations, but I can keep going. I could do it in an even weirder language, but you can still sort of see the 0 to 9, I squared, printed out, right? I can do it in an even weirder language. Okay, this one you can't even see that printed out. But I promise you it's there. Someone who actually programs this language knows what this is doing.
Do people actually program in that language? Please tell me no.
Yes, unfortunately.
Wait, for what?
Mostly mathematicians. I imagine you can tell why. At any rate, completely independent of what language, that same algorithm worked for all of those. It was pretty much the same thing every time. So that's great. We've seen some algorithms. We've seen some pretty basic algorithms. How do we make our own? So as someone pointed out to us the other day, this is the algorithm, right? This is the set of steps to write an algorithm. It's a little bit meta, but that's okay. You guys will get it. So there are 3 main things you have to do. One of them you've been doing since the very beginning of this class. We haven't really thought about it as part of an algorithm, but you've had to do it on every single lab. You've had to do it on every single assignment. You've got to figure out what the input is, what you need to take as input, and what the output is, what you need to print out or what you need to return if it's a function, right? You have to know this before you start. Normally, we tell you what we're going to give you as input or what you should take as input and what we want as output. Sometimes it'll be vague. Sometimes we'll say something like print the change. We won't tell you how. You'll have to figure out, okay, well, what do they mean by print the change? I need to print the number of each coin that was used. We could have just said print the outcome of the rock, paper, scissors, lizard spot game. You have to figure out what the output is. We could say that for the input of that one, you're just going to get choices. You have to figure out, okay, well, how exactly do I get those choices? What does it mean to get a choice? I get some string that's a choice. I get some integer that's a choice. You might have to figure it out. We told you so far because that way we make sure that you guys are all actually writing the same thing and we can grade it and it'll work. And you're not going to go down some weird wrong path that's not going to work, because it's hard to realize that it's not going to work until you've been doing this for a while. But so far we've given you the inputs and outputs. You might start having to come up with some of them on your own. Second thing you have to do is kind of come up with a main idea for how to solve the problem, right? How are we going to go about this? With cashier, kind of the main idea for how we were going to go about this was, well, we can use mod to figure out how much of any given, or like how much money is going to be left over after we make the most change we can with this denomination or this bill. And then we can use integer division, dividing and truncating, to figure out how many of that bill we use, right? So we can start at the very beginning, do this integer division to figure out how many 20s, and then we can do mod to figure out how much money is left, right? That was the main idea for cashier. Everything else after that was details. Then you sort of work out the details, and you go on and you write out each of these steps formally, which is where you would say, you know, step 1, subtract the amount paid from the cost, or subtract the cost from the amount paid to get the amount of change. Step 2, you know, divide by 20 to get the number of 20s. Step 3, mod 20 to get the remaining amount, right? You write out the specific steps that you need someone to follow, that you need your cashier to follow if you're training them later on. But first you need that big main idea of how am I going to solve this problem? For rock, paper, scissors, the main idea was you needed to compare these choices and go through each of these pairs and make sure that you were handling each pair individually, like rock and paper, lizard and Spock, lizard and scissors. You need to make sure that you had a case for all of those. After that, you could go through and figure out how exactly you were going to make that work. But that was the main idea for that one. So I'm actually getting ahead of myself here. After you have that main idea, you can start building up to the specifics. And like I said, the specifics are where you actually write out these specific things that might have variable names in them, or might be keeping track of a particular value, or writing, you know, repeat this many times, or repeat until this is true. So this is all very abstract so far. I've kind of given you some pretty simple examples, and I've given you high-level overview for how you do this. But now I want to walk through this particular example. I'll ask you guys for input, but I don't expect you to be able to do it yet, because this is what teaching is about. I'm going to try to help out and get us to walk through this, but I want you guys to be able to follow along. I want you to see what I'm doing, and even if you might not have been able to come up with it yourself, I want you to be able to look at it and say, oh, okay, yeah, that makes sense. And say, what did I do there? Where did I start? So let's look at this problem. I've got $10,000, and every month I get another $500, and I get 1% interest on the amount of money I already have. What I want to figure out is how many years until I have $100,000. So let's start at the very beginning. For this one, what are my inputs? What do I have to work with? What was that? $10,000. $10,000 is what? Yeah. So that's my starting money. Can you guys read this? Am I writing too small? Maybe? Okay. Do it a little bit bigger. Oh yeah, this one. Okay, so I got $10,000 to start with. What else do I know? I get $500 every month. What else do I know? The interest. I get 1% interest every month. I can spell. Okay, what else do I know?
How long will it take you to go?
To 100,000. I know my goal. My goal is $100,000. Okay. I think that's all the input that I'm given. So you also said what I want to find out, right? So that's the output, right? That's what we need our program to tell us. The output is how many years. Okay, everybody with me so far? Yeah, thumbs up, good. And smiles. Hey, Julie, want to come be Vanna?
Yeah.
Great. We got inputs and outputs. That's pretty much exactly what I had written up there. Okay, so next.
Yeah,
What?
say that louder. Over here you write number of months. Are you looking for years of months?
That's a good point. I said how many years in the problem.
Yeah.
I wrote number of months on the slide. I think my
Probably in the
slide is wrong.
slides.
Good catch. This is why you get someone to proofread your slides. I had someone proofread my slides and it didn't help at all. I had 2 people proofread my slides and it didn't help at all. Okay, so next thing we want to do, next slide. How are we going to solve the problem? Okay, this is where it starts getting tough. What do we need to do to solve this problem? If you were just going to do it with yourself in a calculator, what are you going to do? You'd make an equation. Okay. That's a pretty good idea, right? This is kind of like those problems they put in math class. I don't remember what year of math class that was. Algebra 2. That sounds about right. You get a certain amount of money, you get interest every month. How many months or years does it take to get this much money? There's one small problem. I don't remember anywhere in that problem where you get an extra money each month, which also goes into the right. So that could be complicated to write. I don't know how I would do it. That might take some calculus. Some of the kids who are in calculus might be able to do it. I'm not sure I can do it very top of my head.
Oh, wait, what?
I don't think I could do it off the top of my head. I need to think about that for a while before I wrote out information. So unfortunately, I crafted this problem especially so an equation wouldn't be really easy. So that's a good idea. And that's normally the first thing you should think of. Then you should write code. Okay, fine. But what do I write? In order to tell the computer what to do, I have to know what I would do, right? For the cashier, you know, it's how many 20s can I make with this? How much is left over? You had to figure out how to tell the computer that, but you had to know what you were going to do first. So let's just say you were a human and you're trying to figure it out.
I were trying to figure out something individually, so maybe per month I'll probably add take the percentage off and then do the same thing until I get
Yeah.
the goal.
Okay, right? Okay, so I'm going to rephrase that slightly. You are going to do this over and over. You are going to loop doing the same steps until you hit $100,000, right? So
Also, right on, Jackie. Solid. Solid.
yeah,
Oh, do I go forward?
that was exactly what we had on the slide again. You guys are on tonight. Okay, so that's exactly what you would do if you were a human. That's exactly what you're going to tell the computer to do, right? The only difference is that the computer is just faster at it than you are. It'll spit out the answer in, you know, half a second or whatever. It would have taken you a lot longer, but it's doing the same thing. So what we want to do is, since an equation's really tough, we might be able to figure that out. I'm not sure I can do that in class. I wrote this problem especially because it was hard to do that. So it's easier to just sit through and actually go figure it out. So we can go through every month. We can add $100. We can get 1% interest, and then we can check if we're at $100,000 yet, right? That's the main idea. So now that we've got the main idea, what we want to do are write out steps so that ideally somebody else can write the code for you if they've got all of your steps. That's kind of the goal with this. Algorithms are used an awful lot when people publish research papers, for example, because you might be doing something a little bit differently, but you still want to figure out what they did and see their results. So the algorithm lets you go and copy what they did without copying it literally word for word. It means if they made a mistake when they took their algorithm and translated it into code, and you do it on your own, you might not make that mistake. You might realize there was something wrong with it. It's a little general. So let's go and try and write out the steps for this. So what do I do first? Besides erasing all the crap that's still on the board. If you were sitting down with a pencil and paper, any terms you want.
First, I can have the $10,000.
What was that?
First, the $10,000, and then.
Okay, start with $10,000. Okay, next. That's a good idea too, right? We're starting at year one. Actually, no time has passed now, so I might nitpick and start at year 0, but same idea, right? Start at the beginning of time. We'll add that as step 0, because I forgot that before. Good point. Okay, sorry, but people haven't helped yet. Yeah. Multiply 500 times 12. Okay. That's how much you get in a year.
Yeah.
So that almost works. But the problem with this one is you get interest each month. And the interest each month happens before you get some of those $500. So it actually matters what order we do it in. Otherwise, yeah, right, because we care about years. But we've got months. In this case, we might actually have to go month by month. So good thought, but instead, I think we're just going to pay $500. What do you want to do with $500? Okay. Yeah, sorry.
So I have a question.
Uh-huh.
From the interest we get from the money we have, do we also add that to the next month or just the 500?
So interest always gets added to your total as well. What happens when you get interest in a bank is they calculate how much your interest would be, and then they add that straight back into your account. So the next month when you get interest on your starting amount, and you get interest on your interest. That's compounding interest. So yeah, your interest goes straight back into your bank account. You get interest on that.
So you just add 500 plus the interest you got.
Yeah. Okay. So we got 500. We got the interest we got. So add 500 plus our interest. How do I figure out our interest? 0.01 times okay, to our total. Almost running out of room, but not quite. Okay. What next? I did this once, so now I've got, what is it? $10,600. Now what? Yeah.
So you just said 50% instead considering each 100%.
Okay. Repeat step 2 until total is at least 100,000. Pretty much what you said. I think you can get to the words. Yeah.
If you repeat step 2, you just keep multiplying by 10k. So we have to set
Good catch.
the
So what do I multiply by? That is 10k.
you set 10k as starting value, and then you do 0.01 times the starting value. So then if it adds it, then when it adds it, then that'll add to the original starting value. Then every time you redo it, it'll be more.
Then you're computing with this added amount. So the next month you're saying I wanna take 1% of like 10,600 the second month. Yeah. Okay. So starting value is good. I've been referring to it as total and I'm writing it up here. I think that's just because it's what I'm writing, but yeah. That's exactly right. I thought it was gonna take a whole lot longer to find that. Good. Yeah?
So after step 3, should we say like year plus 1?
After step 3,
So 3 years.
a year has passed. Add 1, 2 years. Okay, so what I'm gonna do now is I start with $10,000. I do this step to add $500 in interest. I keep going on step 2 until I reach $100,000, and then I add a year. Okay, so what didn't work?
Okay, so 4 should go between 2 and
4 should actually be there. So let's make it 2.5.
3, and 3 should be rephrased.
How should 3 be rephrased?
It goes back to 1.
It goes back to 1. What happens if we go back to 1 though?
Oh, you're sure.
Yeah, 1 means we'd start over. We'd have calculated this money and interest, and then we'd go back to $10,000. Okay. So let's take a step back again. Now what we're doing is we start with $10,000, we add $500, and we add our interest. A year has passed, we add 1 year. We go back and repeat. I guess this should be steps 2 through 2.5, right? So we actually want to do those. Okay. So we add $500 in interest, we add a year, and we repeat. We add $500 in interest, we add a year, and then we repeat. And then eventually we hit $100,000. Okay. Do people like this? I got 1 yes, I got 1 no, I got another no, I got a couple of no's. Okay, someone who said no, what don't you like about it?
Should be a month.
It should be a month has passed, not a year has passed, right? Because we said this was every month. Okay. How do I fix that? I can just say
A month has passed.
month has passed. We could say add 1 to month, but I have to change fewer things if I just say add a 12 to year. Why not? It's straightforward, right? A month has passed. Okay. Now who likes it? I see a yes and a lot of blank stares. Okay, so this is essentially what I've got on the slide again. You guys are good. I was planning to walk through this one. Okay. Yeah, just get the whole slide out. Okay, so I called it current total. I called it total up here, whatever. We initialized it to the starting amount, which was 10,000. I might just say the starting amount so that that can be an input and we can calculate this for any starting amount, right? But whatever. We loop until the total is at least the ending amount, which was this step 3 here where we said repeat. And then inside, I add the monthly interest and the flat monthly gain. So I add $500 and I add the interest. And then here I returned months divided by 12. Here you just counted by 1/12 years, right? We essentially did the same thing. That's exactly how you do it. Okay. So, are you guys comfortable with what we just did to solve this problem?
I want to point out that you guys are better than Jeff because you actually wrote down the keeping track of what year it is, which he didn't do.
That's true. I didn't actually count that.
That one is more correct.
Okay. So, are you guys comfortable with the process we went through to do this? Maybe not like do it completely on your own, but you followed what I was doing and it made sense, and like each of the steps made sense, and thinking about it as if you're sitting down with a pencil and paper and actually figuring this out made sense. Yeah. Okay. So, the next thing you would have to do if we were actually programming this, hang on a minute. The next thing you would have to do if we were actually programming this is turn this into code. Show of hands, who would be comfortable taking this and turning it into Java code? Okay, that was a lot more no's, right? So, let's walk through that example.
Where do you want me?
Do you want to project this?
Oh, this?
Yeah.
Yes.
Okay. So I'm not gonna make you guys code along with me. I can type faster than you can because I've been doing this for a lot longer. I just want you to watch for now, and hopefully we'll get more practice with this later. But I'm gonna try and go step by step through how I would turn this into code. So I'm gonna need interest. Copy in a file, get in there, change it to interest. All right. Can everybody see okay? Bigger font, smaller font? We're all good. Okay. So once Julie gets around to presenting, I will have my algorithm right up here on the slides next to me.
Sorry, I'm waiting for the Wi-Fi.
That Google Wi-Fi. All right, well, let's start with your algorithm. Okay. Theirs is better anyway. So let's come back later to do inputs. Let's come back later to do inputs. For now, let's just go through this algorithm like you guys have it. Okay. Start at year 0. What do I do to start at year 0? Set a variable to it. Okay. Int year equals 0. All right. Straightforward so far. All right, next thing we wanted to do is to start with $10,000. Same thing, right? So since money isn't necessarily in increments of $1, I'm going to make this a double because you can have, cents and coins and stuff. So let's just call that money and let's make it $10,000. Okay, everybody happy with this so far? Question? Year would be a double because there's months. Good point. Okay, so I've got year and I've got money. Okay, what's the next step? This one gets more complicated. Add $500 and our interest to our total. All right, I'm going to split this up into multiple lines of code because that's just way too complicated for one line. So let's do add $500 first. Oh, good. We're going to get an algorithm. We're maybe going to get an algorithm. Okay, how do I add $500? What do I want to add $500 to? to money. Okay. How do I add $500 to money?
On the other side.
No, that's fine. Okay. I'm just going to do something like that. I'm going to take money, add $500, store it back in money. Does that line make sense? This is back from the arithmetic we did in week 1. We haven't done a whole lot of arithmetic since then. So if you guys don't remember, that's always a good place to find a refresher, or go back and look at cashier, see what you did there. Okay, adding $500. The rest of that was I need to add the monthly interest. So how do I calculate the interest I'm getting? I see some people saying it quietly.
Plus 20 times 0.
Equals money times, I heard a 0.01 and I heard a 1.01. I think in this case the 1.01 has it, because if I multiply by 0.01, my money is going to be 1/100th of what it was every time. What I want to do is increase it by 1/100th. So I could say this, which would be the same thing, right? Because now I take the money I have and I add the interest. That does the same thing. Okay. Still with me? Okay. And then there was step 2.5 that you guys had and I didn't. A month has passed. Add 1/12 to year. Okay, well, that's the same thing. Year equals year plus 1/12. Except this is Java, so I need parentheses so it remembers to do the arithmetic in the right order and so that I can tell it's doing the arithmetic in the right order. And I need to make sure I don't do integer division. If I do integer division, I'm going to be doing year equals year plus 0. That's definitely not what I want to do. So this is just a gotcha. You'd probably figure it out as soon as you ran your program and realized that year was 0 every time. Yeah?
Why is it 1.01?
Why is it 1.01? Okay, so I did money equals money times 1.01. So what I did was multiply it by 101%. I did that instead of adding 1% of it. So what I could have done is money equals money plus, and I could have added 1% of money. Yeah? Does this one make sense?
Yeah, that's one.
Okay, so
Just leave it like that.
I'll just leave it like that. That's fine. This is more just algebra stuff. It's distributive rule? I don't remember. Something about an algebra. I can combine the 1 and the 0.01 into one thing and make it shorter. That's all. But I'm just adding 1% to money. Okay. So I add 1 month, which is 1/12 of a year, like you guys said. And then step 3 is maybe the hard part, right? Repeat steps 2 through 2.5. So that's this stuff. Repeat that until the total is at least $100,000. How do I do this? I heard ifs. If is going to do it once, if the total is at least $1,000. If doesn't do it multiple times, but a loop will do it multiple times, right? A loop is going to keep going until it's $100,000. Okay. There are 2 ways to start a loop. There's for, which goes over each element in the array. And there's while, which keeps doing your code until some condition is true, or until some condition is false, I guess. It does it while some condition is true. So which one do I want here? I want while, right? I just set a condition. So I'm going to indent this. I'm going to say while. I'm going to start a loop. I'm I'm going to go down here and make sure to end the loop so that my parentheses match up. And now what do I put in while? Money is,
Less than.
well, money is less than 100,000. Do this. Okay. And then, here's one step that I had that you guys didn't have, but that's probably because I cut you off before you got to it. I need to spit out the number of years. Okay, I heard it quietly from a couple of people. System.out.println, year. Okay, so, people happy with this? Yeah, more or less.
Here's some guesses at what the answer is.
21. Don't know. Okay. Let's find out. And while we find out, did everybody follow along with the how we wrote this? Whoops, I'm running the wrong command. Let's run this command. 7.5. No way. I wanna see that happen. I wanna see every time inside the loop. I wanna see how much money I've got. I'm gonna make that look different than the number of years, so I don't think it's printing years. That's a lot of months. That's more months than we thought, right? It's only 7 years, but 7 years is what? 84 months? Something like that?
Yeah.
So, money really did get to 100,000. Nice. That did exactly what we wanted it to. Okay. Did people follow along with how I turned each of those steps into this? Yeah. Okay. So, I'm just going to point this out. Before we did this, I got a bunch of no's for do you see how you would turn this into code? After we did that, you guys are like, yeah, okay, I follow what steps you're doing. So, the only barrier there is just experience. I think the reason that it's not clear and you don't feel confident about going from that to this is that you just haven't done it much and maybe don't know where to start, right? We're here to help you figure out how to start. If you don't know how to start on something, ask questions. We'll help you start, and I am totally confident that once you've got this how do I start down, and once you actually start writing this stuff, it'll flow. You'll look back at the lectures, you'll figure out what to do, you'll ask us some questions, you'll go back and you'll finish the things you know how to do and it'll work. So that's enough of my confidence boosting for now. We'll go back to this. 7:50. Yeah, this would be a good time to take a break. Do we need bathroom breaks, water breaks? Yeah, okay. I guess you don't even need a picture of the board because we essentially got the same thing on the board as we did on the slides.
Well, but I opened up I didn't know that at first, so I opened up just like a document and
typed it in.
Yeah.
That's fine.
Yep.
That was good. These guys are sharp. I was planning on completely walking through that myself. So.
Well, I'm glad we have we seem to be finally concentrating in on a core group of engaged kids.
I think it's all about the type of problems we're solving too, because before when we're talking about Java stuff and coding stuff, everyone's like, I don't really know, and now we're going to problem solving.
Real world.
Everyone's good at problem solving.
Yeah.
It's the coding that.
It's bored. Where's Jackie, Eileen?
Did she let us know that she was going to be here? She didn't let me know. Did we take attendance? We didn't take attendance, did we? Let me do that really quick, when everyone gets back. 19,
Yeah, we got an email.
from Jackie?
Yeah.
Oh, yes, I do remember that. Wait, so today's the 19th, and
Today's the
yet,
19th.
and yet, there's already seems to be attendance taken for today.
I have no idea.
Or, oh,
Go for it.
I'm sure they were left over from a previous meeting.
you want the watermelon one?
Oh, you have the watermelon one? Sorry.
Is it actually?
It's unsweet.
I wonder if Julie took attendance.
I think she started.
Yeah, she must have. So Jorge's not here. Is Jorge still in this class?
No.
So he's dropping and hasn't let us know yet?
Oh, I thought you were, I don't know. We'll see.
Okay, well,
I don't remember if we got an email.
then I'm taking him out.
Edgar sent an email today.
I got
Edgar did, but not Jorge.
Whatever. We'll wait.
But he's been gone. This is like his third absence in a row.
I am happy to teach whoever shows up.
Weird.
Oh, I hate hint water.
Smells like, it smells like.
It smells like
Adulterating my water.
You have to stick with a face, otherwise it just tastes even weirder. Yeah.
Watermelon juice.
But no, we're not gonna do it.
And I think Maggie is gonna drop too. Is Maggie here today? No.
Yeah, they would.
I was trying this out, but it didn't work. That is 12 times.
I can't believe we lost Jorge and Edgar.
There. Actually, not George. Not George. Not George. I guess he has soccer.
I got it.
Yeah, I think Maggie isn't coming anymore either. This is her. Last week she was excused twice. And then this week she's absent twice. So she hasn't been here in 2 weeks. I think she's done.
Sort of like. I do that too a lot. I hear like giant cracks sometimes. I do it during class in the morning, and it's really loud, and people around me are
Yeah. Mine cracks really well if I can get it in the right position.
You're like twisting yourself.
I'd rather it not crack really well because that would mean it would hurt less.
I would try it. This Windows 8
We don't have an assignment this week, right? It's like technically assignment 2,
Tic-tac-toe, I think, is still going
right?
this
Right?
week.
So we don't have a new one.
We don't have a new assignment.
Okay.
We also don't have a new assignment for next week because next week's Thanksgiving week. So you guys finish tic-tac-toe by this Sunday, and then there is nothing to do Thanksgiving week, and then we will come back with another
Or
assignment
those
after
who are behind can get caught up.
that too.
Like those who
Whoa.
didn't turn in previous assignments or whatever.
If you have finished everything and you would like stuff to do for Thanksgiving, pay attention because at the end of class, we will give everybody a game to play for homework next week. A game.
I'll like just look at this.
The other slides are going to be.
What about?
It's, we're gonna go through the same style of thinking, different types of problems, and I think there's gonna be
We're open.
one sort of concept bit that we haven't gotten to already, but it's pretty well laid out in the slides. You'll also be able to see the video, also be able to ask us, but you'll pick it up on your
I could
it's,
just access Why does Google have free candy like
to make all the employees happy. Okay, so while I think all of the students are here, even if the other instructor and the admin aren't, some logistics stuff for next week. Next week's Thanksgiving week. There is not going to be an additional assignment Thanksgiving week. So finish up tic-tac-toe by this Sunday. If you
hopefully.
if you don't manage to get lab 4 done, hopefully you'll have time to catch up on that next week. Question?
Do we actually have a lab 4 this week?
There is a lab 4. Did it not show up? The lab 4 is not required for tic-tac-toe. It's just a lot of practice with loops and algorithms because those are all new.
Do we have a lab next week?
No. Next week, if you haven't finished lab 4 yet, use that time to catch up on lab 4. In addition, next week, since Thursday is Thanksgiving, there is no class on Thursday. And because it's a half week and we didn't really know what to do, Monday's going to be a guest lecture. Julie announced us on Piazza. We're bringing in our roommate, Ryan Evans, who works at YouTube. And he's going to give a talk about how all of the code stuff you're doing right now fits into the real world and kind of what you have to do to get from the kind of programs that you're writing to, quote, real programs that do something fun and interesting.
That sounds awesome.
So it should be a real interesting talk. I've seen some of the things he's going to talk about, and it looks real fun. I won't spoil it. I want to let him have all the fun.
Also, those of you who have been very overloaded and have not had a chance to do all of the labs or to finish all of the assignments, I highly encourage you guys to use next week, which there's no new assignment, there's no new lab, there's no nothing, to use next week to get caught up.
Yeah, it's a great time to catch up, and we're still going to be in town and answering questions, so ask away. I think so far we've had a decent track record. With a couple of exceptions, we've answered most of the questions in like half hour or less. So that's about the time window to look for, I think. If you just feel like sending something off and then coming back to look at it later. So that being said, we'll get back to the actual class now. So I think what I have for the rest of the slides is we're going to go through a couple more examples of how to do this stuff, just for practice really at this point, because you've already seen the meat of today's lecture. So next thing we're going to do another example that's kind of similar to the last one. So the problem this time, do you want to either present from there or come over here again? Or do you want to write? Either one. Okay.
I don't care.
Okay, you can come over here. Okay, so this is a problem I think that might be on one of the labs. I don't remember. Or did it used to be on a lab and we took it off?
It's on a lab somewhere.
It's on the lab somewhere. Okay, good enough for me.
I don't remember which.
So this is also one of the lab problems. We're going to walk through it now, see if we can figure it out. So the problem is I've got this array of integers. So this is what I said. I've got a bunch of integers in a row. I need to find the largest one. If you have trouble translating this to something that you would do by hand, think about I have a bunch of numbers written out on index cards. I've got a stack of index cards, and I need to find the largest one and report what the largest one is. So, inputs and outputs. Whoops. This one should be pretty straightforward because it pretty much just said it in the problem description. Input. Integers, bunch of integers. Output. Integer, the largest one. Okay, good. So, good idea. How do we solve this one? If you were doing if I can, how do you solve this? What would you do? You've got a stack of index cards, say. You look at the top one, you can sheaf through it. How do you figure out what the largest one is?
Actually, well, can you like lay them out?
Can you lay them out and look at all of them at once? I'm gonna say no, because one, that requires a great ability to multitask and look at everything, and two, there could be a lot of instances. So let's say that you can, say look at a couple of them at once and you get sort of spread out, but you can't look at everything at once.
Do we know how many index cards there are?
Sure.
Okay, so what I would do is I would tally every time I go to another index card, I would tally that single index card. And then I would set that value to, let's just say starting value. And then if I find a greater value, I would set that value to starting value. And then when the amount of cards I go through reaches.
Okay, hang on a minute. Great answer, but too much detail. Can you step me back a little and give me like an Englishism?
So I basically find like what a greater value is.
Okay, I'm going to rephrase that and say you're going to remember the largest thing you've seen so far, right? So that's the main idea here. The main idea is look at all the index cards. I'm going to rephrase, leap over all the integers, and then remember the highest value you've seen so far. Okay. So then you also started doing a bunch of detail about how you actually do that, right? Yeah. The how you actually do that is when you go out to write the step-by-step. So in the interest of getting other people involved, somebody else want to help me write the step-by-steps? What do I do first? What's the first thing I do?
Compare the first to the second one, see which is bigger.
Okay. What do I do based on which one's the biggest?
Compare it to the next one.
Very
Third
next. Compare the result of one to the next one, which is the third. Okay, then what?
And the winner advances.
Winner advances. Okay. So the way I want to, essentially what I want to do here is write dot, 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 right? I want to say, okay, and then compare the winner of that to the fourth, and then the winner of that to the fifth, and then the winner of that to the sixth, and sort of keep going like this, right? Dot, 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 while it's a great way of saying keep going, isn't quite precise enough. So at least in English, what can I actually say here that would be repeating this? It's a hard one. let me phrase it for you guys, because I've had a little more practice. Until we reach the end of the integers, continue comparing the winner of the previous comparison to the next integer and keeping it. Does that make sense? A little wordy.
Could I say repeat step 2 for each item in the array?
Sure. Okay, so I did this over and over. I compared them. I took the winner. I compared the winner to the next one and took the winner. I compared the winner to the next one and took the winner. I did this. I finished all the integers. Now what do I do? Now theoretically, I've found the biggest one because it was the one that came out on top. So all I want to do at this point is return it to you guys. I've got the biggest one. I'm going to give it back. I'm done. That was it. So as the last thing, I want to return and or print the final winner. So you'll be pleased to know that this was actually something completely different than what I came up with. Well, not completely different, somewhat different. So let's go through my example just to see how it was slightly different.
Jeff,
What?
minimum.
Oh my gosh.
My proofreaders were really not on top of their stuff.
There were 2 of us. Matt and I both proofread this.
They made lots of comments and none of them fixed that problem.
Okay.
Okay, so.
Were you done with this?
Yeah. Go to the little main idea. Okay, so yours, you guys, well, Colin, I guess, took these 2 integers at every single comparison and kind of fought out and kept the winner. I forgot your name. Jordan. Okay. I still don't know everyone's names yet. This is a problem. Jordan's example, I think if I understood it correctly, was more similar to mine, where you kind of keep track of the highest one you've seen so far. You don't sort of fight it out every time, but you just sort of repeatedly check, is this higher than anything I've seen yet? And then you only keep track of the very highest one you've seen. Effectively, they do the same thing. It's just worded slightly differently. So when I wrote out the steps, keep going. I had this problem. Yeah. So when I started the loop, I didn't know what the maximum I'd seen so far was. When Colin started the loop, he just started with the first and second elements, right? That made a lot of sense. One of them was going to win. Sure. That made it really easy. That's all you have to see. I had this problem with, I don't know what the thing I've seen so far is. If I go onto the first element of the loop and I try and compare it to what? 0? Yeah, can't slide. If I start with 0, then if every integer in this array is negative, then I'm going to end up saying that like 0 was the biggest number I've seen so far. And that doesn't make a whole lot of sense. This is kind of abstract right now. But let's say the integers I was looking at were like -5, -10, and -30. If I started out here and said, okay, well, when I go and compare -5 to the biggest thing I've seen so far, well, let's just bootstrap myself and start with the biggest thing I've seen so far is 0. I'm going to go through and compare it, and the biggest thing I've ever seen at the end is still going to be 0. So Colin avoided this problem by just saying, well, the biggest thing I've seen, let's just start with the first 2. Out of these, -5 wins. And then you compare it to the next one, and -5 still wins, and you get -5 is done. So I had this problem, and what I had to do is say, well, I'm going to fix this by just making starting with negative infinity, because nothing's lower than negative infinity. I'm not going to run into this problem. Negative infinity, you might say. Yes.
How do you write that?
How do you write negative infinity?
Just like that.
Just like that. It's a programmer's job, right?
Oh.
Some programming languages, you have to figure out how to do negative infinity yourself. You have to say, well, how can I hack around this to figure out a way to make it seem like I'm doing negative infinity? Other programming languages, you know that really weird mathy one that you saw? I'm pretty sure you can actually write negative infinity. I think that's actually possible in some programming languages. So it's up to the programmer. You'll figure out some way to represent negative infinity.
What is it in Java?
What is it in Java?
Yeah.
The closest you can get to negative infinity in Java is to write out like integer.minint or something, which is the minimum possible integer Java can represent. Of course, your workaround if you were writing this in Java might just be to use Colin's solution, which is pretty similar, and not worry about getting this max so far at all. You might just start with the first element or the first and second element and see which one's good. So when you go and actually do this in a programming language, you got to figure it out. Did everyone follow this example? Yeah. Okay. I'm going to skip the code for this one, but maybe we'll write it up in that class examples directory later and push it out in the next wave of the writing. Okay, new example. Really tired of erasing. For this one, we've got another list of integers. This time we know it's sorted, but we want to find some particular integer.
What does sorted mean?
Sorted. Sorted means they're all in ascending order in this case. So like, I've got a list, -5. What? Someone say something? No? Okay. And 30, 45. The next one cannot be 1 because that would be less than the one before it. It wouldn't be in ascending order. So let's make it 61 and then 1028. So let's say I've got these and I want to find which index in the list 45 is. So this is pretty easy for this example, right? What's the answer? 3. Yeah, because we start at 0. Okay. How'd you know? 4 is close enough for doing it in English and on the whiteboard, but it's 3. So now, same thing as the last problem. What if you can't actually look at everything at once? If this is your stack of index cards, what if it's 1,000 index cards deep? Yeah.
What does find the index mean?
What does find the index mean? So I'm looking for 45.
You just have a number that you're searching for.
I have a number that I'm searching for. It's some particular integer. So in this case, I said this particular integer I care about is 45. And I want to find it in the list. And I want to return the index in the list so that somebody else can jump straight to it.
Sorry, position.
Position, yeah. Index is position. Those words are synonyms for our uses. Good question. Where was I? Right. So when it's right here on the board, it's real easy. You just say 3, you're done. What if this stretches all the way around the room? What if this stretches into the next room? What if you've got your index cards stacked like 50 deep? What do you do? Cry. Well, that is one solution, but it probably won't help you find the index of 45. It might help, I don't know. It might help with some things. Okay. This one has, well, no, let's start and just go back. Okay, I've got a stack of index cards. I'm looking for 45. What do? I make a loop, which means I'm going to repeat some action. What action do I want to repeat?
Search. Find.
I look. What do I look at?
index cards.
Okay. I'll look at the top one. The top one's the one I can see, right? What do I do?
Okay, so that's not 45. You move on to the next one, so you add 1.
If that's not 45, I check it, I add 1 to my index, and I move on. I look at it again. It's not 45. I check it, add 1. Advance a couple of slides.
I don't know how to.
Down, right, anything. Space. You already got past that. Sorry.
Did you
Yeah,
want
we'll
to?
skip it.
Okay.
Okay, so exactly what you just said. We go through one by one, we check. Is it X? Is it the integer I'm looking for? Nope, check it. Next one. Is it the integer I'm looking for? Nope, check it. Next one. Okay, so we could write out the steps for this. I'm gonna skip it because this is pretty straightforward and you guys have already done 2 examples. Is that okay?
Do you want to just talk them through yours?
Okay. So what I did for this one is I did essentially what you just said. I'm going to make a loop. I'm going to go over every integer in the array. I'm going to look at it. If it's equal to x, I'm going to immediately return, spit out the current index, and be done. That's it. I print, I return, I exit. That's it. If it's not, I check it and I move on to the next one and I just go on to the next iteration. In my example, if I get to the end and I've gone through every single integer in the array, I've gone through every single index card in my stack, I still haven't found x. Like if I was looking for 37 in this one, if I go through and say, well, that's not 37, that's not 37, neither is this, or this, or this, or this, and I got all the way to the end, then I'm just going to spit out -1 as a way of saying, like, well, I didn't find it, and it's not there, so I don't know what to give you. And you asked for an integer, so I'm just going to give you some integer that will represent it's not there, because there is no -1 of an array, so you can't mistake that for anything else. Not really important. The point is, this is where algorithms come into play. I think we can do better than this. If you had an index card stack that was 1,000,000 cards tall, and the card 45 was the second to last one, you would have to sit there one by one, going through the first 999,000 index cards, right? You'd have to just spin and say no, 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 and eventually you get there. If you had, basically this would just take forever. I think we can do better than this. The reason I think we can do better than this is there was this little trick. I said that this list or this array was sorted. The numbers are in order. I think I can make use of that. I think that if I know they're in order, I can come up with some smarter way to do this. And this isn't one that I expect you guys to come up with. This is something that somebody really smart a long time ago came up with. And students these days learn about it because it's
I think they can
clever.
come up with it.
You think they can come up
I
with it?
can prompt them
Okay.
to come up with it. What if I give you a dictionary and I tell you to find a word? It's in order, right? It's got a bunch of words in an order that you know. And I say, go find the word, I don't know, zebra. What do you do?
Go to the top right, or at the last
Okay, what if
There's no little
paraphrase-
tabs on the side that show letters. You just got a big book.
what if it's a book and you don't, if it's a book of ordered words, but you don't know if it goes through the whole alphabet or just part of it. So I tell you to look for aardvark, but you don't know if it's a whole dictionary or if it's the A book of the encyclopedia. But you know that it's in order. Does that make sense? Similar to how with these numbers, you don't know where they start and end, but you know they're in order. What would you do?
Would you, for example, look at the very first word and check if that was zebra? And then if it's not, go to the next word. And look at the second word and check if that was zebra. That's not how you use a dictionary.
Do you guys not use books? Is that the problem?
This might be dated.
Control F.
Control F.
I think we're too old for this version, Julie.
Like what I would always do is I would open to a random page and then I would spot check, am I before or after it? Does that make, do you guys do that or is that really not a thing that you do?
Ignoring how well.
Answer.
Give an answer. Okay, even better.
Look at the first and last word, go to whichever one it's closer to, cut it in half. Do the same, cut that in half, and then just keep cutting it in half until you get to what you're looking for.
Do you want to take that one or do you want me to take it?
Meaning answer or?
Do you want to just go on to the next slide or do you want to call that close enough?
It was very close.
Okay.
I would leave it at that. That was very close. The only problem with your algorithm is that we don't actually know how spread out these numbers are. And so you can say which one it's closer to, but for example, if you had, yeah, can you give us an example? And then 100 or something.
2000.
There you go. So if this were our data set, it's in ordered, it follows the rules. But if we were looking for 5, you would have gone to the wrong end, right? That's the only problem. But other than that, it's very, very close. So you had the right idea, but there's one detail that caused you to go the wrong way there. So go on and show them.
Yeah. So your idea was you got to look at the first and the last, right? So in the example that we came up with the pictures for, because I'm too lazy to write my own pictures, you look at the first one, it's 20. You look at the last one, it's 67. But you also look at the middle. So in this case, I'm not just figuring out whether 37 in this example is closer to 20 or closer to 67, but I'm figuring out which half is it in. Is it between 20 and 45, or is it between 45 and 67? If it's a dictionary, is it between A and K, where I randomly flipped open to, or is it between K and Z? So in this case, 37 is between 20 and 45. So I know I can ignore the whole second half of the list. Next slide. Okay, now I do it again. This time, there's not an easy middle point, so I just have to pick one of the two that's in the middle. So I got 20 to 35, and I got 35 to 40. Well, 37 is between 35 to 40. So I got to ignore that left side. So now I look at these, I'm down to 2. I've essentially found 37. So at this point I say, well, 37 is one of my boundaries. I'm looking for 37. I found it. I'm there. So I didn't actually look at the whole list. The only things I looked at here were 20 and 67 on the first try, and 45. And then I looked at 35 the second time. And then I looked at 37 and 40. There was this whole side of the list I didn't look at. Sure, it was in the first half, and I did look at 20, 35, and 37, but what if 37 was like the second to last element? I would have skipped almost everything before it. I would have gone pretty much straight there because I just cut it in half every time. Next slide. Do I actually walk through the algorithm here? Oh, okay.
Do you want me to skip forward?
We'll skip forward and come back to it because we're low on time. Okay, so this was complicated. It was hard. It was something that you guys maybe sort of almost got. It wasn't straightforward. The straightforward one was just, okay, well, look at each of them. If it's that, return the index. If it's not, keep going. That was the straightforward basic one. This one was harder to come up with. If we'd actually gone through writing it, it took longer to write. It was harder to write. It had more steps. There were more places for you to mess up. It's hard to say that it's actually correct and you're not going to accidentally ignore the number you're looking for, right? What actually makes this better? It's faster. That's really it.
Do you want your chair?
No, I'm going to stand anyway. That's really what we care about. Like I said, if we were just looking for 5 in this list, if we're doing this linear search and going through each one, we go 5 times. If we're doing this binary search where we split it in half, We get rid of half of it, binary. We only do 3 times because the first one, 2 or 3 is in the middle. The second one, something else is in the middle. The third one, we narrow it all the way down to 5. But if our list is really, really long, like it's 10,000 long, linear search, we'd go through everything to find the last one. Binary search, we only actually have to go 14 times. This is less than 1% of the time. Huh? Well, okay, maybe poor example. Let's say we were trying to find 9,999. The very worst case you could do is going 14 times. Because if you cut it in half every time, once you've cut it in half 14 times, there are only 1 or 2 things left. It doesn't matter what number you're looking for. If you cut it in half 14 times, and you're always cutting out the half that you're sure doesn't have that number in it, it doesn't matter what your number is, you have found it. You might find it earlier than that, but you will never find it later than 14 times. That's just something you could never do going through these cards one by one. If you're curious why it's 14, welcome back to, I think, pre-calc. This is logarithms. If you split it in half every time, you're looking for the power of 2 that is just larger than the length of your list. Because if you multiply the length by 2 and then by 2 again and then by 2 again, that's equivalent to splitting it in half, splitting it in half again, and splitting it in half again. So 10,000, or log base 2 of 10,000 is 14. This is a whole lot faster than going through it one by one. And in the real world, fast matters. I picked the first example I found searching this online. It was actually an article written by Google where they say that speed is king. Speed is super important. The example they had in that article, which I have linked in the slides if you want to read it later, is there was this website called Shopzilla. Their website loaded slowly. Back in the ancient days, whenever this was, it took 7 seconds to load their initial web page. So they spent a little bit of time and they made their code faster, used some better algorithms, improved some other things in there, and they got it all the way down to 2 seconds. So this was huge. The difference it made was they actually got more money. More people stayed on their website and more people explored it because it went faster, right? It seemed snappier. You've probably seen this with apps. If the app sits there and spins for a long time or hangs, you're like, whatever, I'll do something else, I'll find a better one. If it's snappy and fast, you're like, I can keep using this, whatever. Just scroll to the next image and the next image and the next image, and you never stop. On a shopping site, this means you buy more things. The other thing is having faster code means that it runs faster and it takes less time on your computers or your servers, which are essentially big computers dedicated to doing whatever you tell it to do over and over. It takes less time on the server to actually run. And if it takes less time to run, sure, maybe it only went down a little bit, but over hundreds and thousands of people visiting your website, those little bits of time add up. And just in electricity costs and costs of like cooling the computer, because industrial strength fans cost a whole lot too. Just for the costs of running that code for less time, they cut their costs by like 50%. So fast code is important. Because fast code is important, good algorithms are important. Good algorithms are what I look for pretty much whenever I'm interviewing someone for Google. That's the primary thing I care about. If they happen to not be able to write Java code and they can write it in some other programming language, or they make some syntax mistakes and they mess up, I don't really care. If they've got good algorithms, that's the primary thing I'm looking for. Maybe I don't really care is too strong. I don't care as much. So you should at least understand the difference between these on a basic level. For this class, we're probably not going to come after you if you happen to write something that's a slower algorithm than a different algorithm, as long as you can actually do it. I think for the first assignment after Thanksgiving, will specifically ask you to try for something with a good algorithm, just as practice. But other than that, we don't care so much if your code runs in 2 seconds or 7 seconds. But you should understand the difference between these two algorithms, why they're different, why one is faster than the other, why you might want to use the faster one, and why the simple one is still easier to write and figure out what's going on. I kind of ran through that because we were running low on time, but is everybody still with me? Questions or repeating part of it? Good? Good, or reading things? Okay. I don't remember what else I had left. Just recap. So go back to these slides. If you don't remember where to start, go back to the slides. Think about how when we were solving this problem, it was always, okay, well, you don't need to start with how do I make Java do it? You need to start with how would I do it? Because when you think about how would I do it with a pencil and paper, or how would I do it with, if you have an array, a bunch of index cards stacked where you can see the top one. If you can think about how would I do it, then you can go from there to how did Java do it without trying to think about the big picture at the same time. If you're trying to think about the big picture and the Java at the same time, it's going to get real confusing. Go one step at a time. Think about how would I do it, get the big picture down, go from the big picture to these individual steps where we wrote out one by one in English what we were going to do, and then go from that specific English to your code. Things will be a lot easier to figure out. For this lab and assignment, like I said, well, I guess not this assignment, for the next assignment, for this lab, for lab 4, we're going to make you write algorithms because we want to see you do it, and it's important, and you should learn it, and we want you to get feedback. If you haven't already asked, we want you to get feedback on how you're writing them. But pretty much from here on out, writing algorithms will make your lives easier. And I think you saw this when we were writing stuff up on the board, right? You guys were kind of like, well, I don't really know how I'd start. We wrote it up in English. We got to writing the code. Each individual step of that, you guys are like, yeah, okay, I get that. It was just the whole picture that was tough to start or get going. So writing the algorithms helps, even if it seems like it's a waste of time. It's rarely a waste of time. So we're pretty much out of time, but before we go, questions on anything today? It looked like everybody was pretty much getting it, which is good. But this is the complex critical thinking part. So if you don't get it and if you have problems with it, ask questions. Ask questions next week when there's nothing new assigned. Yeah, this is the important part to learn.
This is like real computer science, you guys.
Yeah.
Like this isn't like, dummy class problems. Like algorithms is the core of computer science. This is literally what we have people do in interviews for Google. This is like the major tests in college, etc.
Yeah. So cool. That's it for class. So you guys are all set to go. Thanks.
Thank you.
Grace was impressed today.
I appreciate your applause, Grace.
Thank you. I live for the applause, you might say.
Is that a Lady Gaga?
Yeah, I was gonna say that.
You missed
I was
Julie's
not expecting
One
that out of
Direction.
Jeff.
Yeah, I know. I told her out there she'd do it like